Now, the only thing that you're missing, I think, you've got the math, is the intuition for what the heck is this reactive power. You know what the average power is. The average power delivered to a load is how much real work it's doing on average. But what is going on with this reactive power? So let me just talk quickly about what reactive power means intuitively. It's the power that's, yeah, my handwriting is terrible. It's the power that is shuttled back and forth on the transmission lines rather than going to the load. So let me give an example in limiting cases of these cases we worked out down here. Let's start off with a purely real load. You've got a purely real load. You've got AC power going into your purely real load. When the voltage waveform is positive, your current waveform is positive, there's real work being done by your resistive load. It's heating up, it's doing something. Maybe this resistive load is actually a heater and it's providing warmth. Maybe it's a special type of motor that looks completely resistive and it's producing a torque that's driving machinery. No matter what cycle of the waveform is active, there is energy being delivered to the load. Now let's take an example of an inductive load. This is the most common type of actually occurring loads in industry. It's because most loads in heavy industry are from large electric motors, and these large electric motors are powered with big loops of wire that create electromagnets that make the motors move, but these electromagnets have a lot of inductance to them. So if our load was hypothetically purely inductive, then during part of the voltage waveform, you're creating a magnetic field around this wire and it's not doing work. Let me try that again. During part of the voltage waveform, it's creating a growing magnetic field around the wire and it is doing work. It's storing that energy in the magnetic field. And then during the next part of the cycle of the voltage, that magnetic field is collapsing and the field is doing work under power transmission. So during part of the cycle, your transmission lines are delivering power, are delivering real energy to your motor and to your inductor. And during the second half, the inductor is delivering energy back to the power lines, back to your generator. The average is going to be zero work. Your power factor will be zero. The real part of your S phasor will look something like this for a purely inductive load. The real part is zero, and all of the energy that's that you're seeing being shuttled back and forth on these power lines is just going back and forth in these power lines. None of it's going to your load. Power companies hate this. Oh, and let me just finish up the example. Our first example, when it was a purely resistive load, would look like this. Our purely inductive load would look like this. So this one would be a pure resistor, and this would be a pure inductor. Power companies hate inductive loads because they can't charge you for power that you are not, they can't charge you for energy that you're not using. And if you have a purely inductive load, you're not using any real power. If they had a power meter on your industry, it would be reading zero with a purely inductive load. As much power is being delivered as is being absorbed. As much power is being delivered to your load as being delivered from your load. The problem is the power company is losing power because it's shuttling that energy back and forth along its power lines. Those power lines have resistive losses. And so your power company is losing money and it's not able to bill anybody for that money. Because of that, the power company only likes to see companies that have power factors of 1 or really close to 1. And they'll actually they'll find companies that have power factors that are not close to 1. If you've got a company, if there's a industry that has a power factor of its load that looks like 0.85, I promise you they're getting slapped with a heavy fine from the power company, because the power company wants to somehow recoup its losses from all that reactive power that's being sloshed back and forth from the transmission lines, but isn't showing up on that company's power watt meter as being actually used. So reactive power is that portion of the power that's sloshed back and forth that's not used. That's this vertical axis here. And real power over here is the horizontal axis. That corresponds to the amount of power that's delivered to a resistive load that actually participates in doing work. And where in that world you live is this complex power phasor. So again, just before we go, any real world problem, firstly, figure out what the voltages are and the currents are, like we did in the upper right. Then use these relationships in the lower left to find the complex power phasor. And then you can start answering the questions about how much real power is there. It's the real part of S. How much reactive power? It's the imaginary part of S. What's the apparent power? It's the magnitude of S. And what's the power factor? It is S. What's the angle? It's the difference between the voltage phasor and the current phasor, the voltage phasor angle and the current phasor angle. And what else might you be asked to find? Let's see, the power factor is the cosine of the difference of the angle. The angle of your complex power phasor is from up here, the difference in the angles between your voltage and current phasors. Once you find that power triangle, you found everything.